Tonight, you're going on a journey into the cosmos. Imagine you're 25 years old, standing on Earth, looking up at the stars. You have one lifetime ahead of you. 60 years, maybe more if you're fortunate. 60 years of being awake, alert, experiencing the journey. You board the fastest spacecraft humanity can build. You say goodbye to everyone you know, and you point it toward the stars. The engines fire. Earth falls away behind you. You're heading out into the cosmos. The question we're going to answer tonight is simple but profound. When your journey ends decades from now, when you've lived your entire life aboard that spacecraft, how far from Earth will you be? Which stars could you actually reach? Which worlds could you actually visit? Could you make it to Alpha Centauri, our nearest stellar neighbor? Could you reach further, to stars with potentially habitable planets orbiting them? Or are you confined to a small bubble around the sun, unable to escape our immediate cosmic neighborhood, no matter how long you travel? By the end of tonight, you're going to know the answer. You're going to know exactly which destinations are within reach of a single human lifetime, and which ones remain forever beyond the horizon. And once you know that answer, you'll never look at the night sky the same way again. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. First, we need to establish what we mean by a human lifetime. The average human lifespan today is about 77 years globally, closer to 80 in developed countries. But we're not talking about someone starting a space journey at 75. We're talking about someone leaving Earth young, maybe in their 20s or 30s, and traveling until they die of old age. So, let's say we have 60 years of travel time. 60 years where a spacecraft moves through space carrying a living human being. That's our window. That's what we have to work with. Now, the obvious next question is how fast can that spacecraft go? And this is where things get interesting, because the speed of your spacecraft determines everything. Double your speed, and you double the distance you can cover in 60 years. Increase your speed tenfold, and you increase your reach tenfold. Speed is everything. So, what's the fastest speed we can actually achieve? The fastest spacecraft humans have ever built is the Parker Solar Probe, launched in 2018 to study the Sun. At its closest approach to the Sun, using the Sun's gravity to accelerate, Parker Solar Probe reached speeds of about 430,000 miles per hour. That's roughly 119 miles per second. It's unimaginably fast by everyday standards. If you could drive at that speed, you'd circle Earth in about 2 minutes. You'd reach the Moon in about 35 minutes. But here's the thing. That speed, as impressive as it is still only about 0.064% of the speed of light. Light travels at about 671 million miles per hour. Parker Solar Probe, our fastest spacecraft, is moving at roughly 1/1500th the speed of light. It's barely a crawl compared to light speed. If you took a journey at Parker Solar Probe's maximum speed and traveled for 60 years, how far would you get? Let's do the math. 430,000 miles per hour times 24 hours per day is 10,320,000 miles per day. Times 365 days per year is about 3.77 billion miles per year. Over 60 years, that's roughly 226 billion miles. But let's put that in context. The nearest star system to our Sun is Alpha Centauri, about 4.37 light-years away. A light year is the distance light travels in 1 year, which is about 5.88 trillion miles. So, Alpha Centauri is about 25.7 trillion miles away. At Parker Solar Probe's speed, covering 226 billion miles in 60 years, you'd travel less than 1% of the distance to Alpha Centauri. You'd still have more than 99% of the journey remaining. You wouldn't even get close to leaving our solar system in any meaningful sense. The heliosphere, the bubble of charged particles and magnetic fields that the Sun creates around itself, extends roughly 123 times Earth's distance from the Sun. That's about 11.4 billion miles. You'd pass beyond the heliosphere after about 3 years at Parker Solar Probe speed. But then you'd enter interstellar space, the vast emptiness between stars, and you'd spend the next 57 years of your life crossing a tiny, insignificant fraction of that emptiness, still firmly trapped in the Sun's neighborhood. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. It's about 15 billion miles away, traveling at roughly 38,000 miles per hour. At that speed, it would take Voyager 1 about 75,000 years to reach Alpha Centauri if it were headed in that direction, which it's not. Voyager's journey has been extraordinary. It's been traveling through space for nearly 48 years now. In that time, it's passed Jupiter, Saturn, and entered interstellar space in 2012. It's still sending data back to Earth, incredibly, though its power is slowly fading. The plutonium in its radioisotope thermoelectric generators is decaying, producing less heat and therefore less electricity. By the 2030s, Voyager 1 will no longer have enough power to operate any of its instruments. It will go silent, but it will keep drifting through space at 38,000 miles per hour for millions of years, maybe billions. A dead relic of human technology floating through the void. But in all those decades of travel, covering 15 billion miles, Voyager 1 has barely left the solar system. I mean, it's left the heliosphere, yes, but it's nowhere close to any other star. It's in the interstellar medium, the sparse gas and dust between stars, but it's still gravitationally bound to the Sun. It would take tens of thousands of years to escape the Sun's gravitational influence completely. Voyager's trajectory illustrates the problem perfectly. Even our most successful, longest-running spacecraft, launched with the most efficient trajectory we could design, using gravitational assists from multiple planets to gain speed, is still crawling by interstellar standards. It's moving fast enough to escape the solar system, but nowhere near fast enough to make interstellar travel practical. Let's talk about why current spacecraft are so slow. It comes down to the rocket equation, a fundamental relationship in physics that governs how rockets work. The rocket equation, also called the Tsiolkovsky rocket equation, after the Russian scientist who derived it in the late 19th century, tells us how much speed a rocket can gain based on its fuel and engine efficiency. The equation says that the change in velocity a rocket can achieve is proportional to the exhaust velocity of its engine multiplied by the natural logarithm of the ratio of its initial mass to its final mass. In simpler terms, the more fuel you carry and the faster you can eject that fuel out the back, the more speed you can gain. But here's the problem. Fuel has mass. The more fuel you carry, the heavier your rocket is at the start. And the heavier your rocket is, the more fuel you need to accelerate it. This creates a vicious cycle. To go faster, you need more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that mass. Very quickly, You reach a point where you're carrying so much fuel that most of your fuel is being used just to accelerate the rest of the fuel, not the payload. Chemical rockets, like the ones we use to launch satellites and send probes to other planets, have relatively low exhaust velocities. The best chemical rockets can achieve exhaust velocities of about 2.8 miles per second. That's good enough to escape Earth's gravity and travel through the solar system, but it's not good enough for interstellar travel. To reach even 1% of light speed using a chemical rocket, you'd need a mass ratio, the ratio of initial mass to final mass, of about 1, followed by 64 zeros. That means for every kilogram of payload, spacecraft, crew, equipment, you'd need 10 to the 64th power kilograms of fuel. That's more mass than exists in the observable universe. It's physically impossible. Chemical rockets simply cannot achieve interstellar speeds. The physics doesn't work. Ion drives are better. Ion drives work by ionizing atoms, usually xenon, and accelerating them using electric fields. The exhaust velocity is much higher than chemical rockets, up to about 56 miles per second for some designs. But ion drives produce very low thrust. They can run for years, gradually accelerating a spacecraft, but the acceleration is tiny, fractions of a millimeter per second. It would take decades or centuries to reach interstellar speeds using an ion drive, and you still have the mass ratio problem, just less severe. To reach 10% of light speed using an ion drive, you'd need a mass ratio of about 30 million to 1. For every kilogram of payload, you'd need 30 million kilograms of fuel. That's better than chemical rockets, but still completely impractical. You can't build a spacecraft that's 99.999% fuel by mass. The fuel tanks alone would weigh more than the fuel could accelerate. So our current spacecraft technology, even our absolute fastest and most advanced probes, can't get a human to another star in a lifetime. Not even close. To reach even the nearest star in 60 years, you'd need to travel much, much faster. Let's figure out how much faster. Alpha Centauri is 25.7 trillion miles away. To cover that distance in 60 years, you'd need to travel at about 428 billion miles per year. That's about 49 million miles per hour, roughly 7.3% of the speed of light. That's still much faster than anything we've built. Parker Solar Probe's 430,000 miles per hour is only about 0.88% of what you'd need. You'd need to go more than 100 times faster than our fastest spacecraft just to reach the nearest star in a human lifetime. And Alpha Centauri is the nearest star. If you wanted to reach more distant stars, interesting stars with potentially habitable planets or unique characteristics, you'd need even higher speeds. Barnard's star, about 6 light-years away, would require speeds of about 10.9% of light speed to reach in 60 years. Sirius, the brightest star in our night sky, sits about 8.6 light-years away. You'd need to travel at roughly 14.3% of light speed to get there in 60 years. Vega, a bright star, about 25 light-years away, would require speeds of about 42% of light speed. And anything beyond that, any star more than 30 or 40 light-years away, would require speeds approaching or exceeding half the speed of light. The nearest potentially habitable exoplanet we know of is Proxima Centauri b, orbiting Proxima Centauri at 4.24 light-years away. Proxima b is roughly Earth mass and orbits in its star's habitable zone, the region where temperatures could allow liquid water. We don't know if it actually has water or life, but it's potentially habitable. To reach Proxima b in 60 years, you'd need to travel at about 7% of light speed. But most of the known potentially habitable exoplanets are much farther. TRAPPIST-1, the system with 7 Earth-sized planets, sits 40 light-years away. To reach it in 60 years would require speeds of 67% of light speed. Kepler 452b, a potentially habitable exoplanet orbiting in the habitable zone of a star similar to our Sun, is about 1,400 light-years away. To reach it in 60 years would require traveling at over 99% of light speed. So, which of these destinations could we actually reach? What speeds can we realistically achieve? Let's start with what we have right now. With current technology, chemical rockets, and ion drives, a human couldn't reach another star in a lifetime. We showed that already with Parker Solar Probe. Even our fastest spacecraft would take 75,000 years to reach Alpha Centauri. You'd spend your entire 60 years traveling and barely make it past the edge of our solar system. So, with the technology we have today, the answer is 0 light years. You can't reach any other star in a human lifetime. But what about technology we could realistically build in the next few decades? Nuclear propulsion has been designed and partially tested since the 1950s. We know how to build nuclear rockets. The engineering exists. We just haven't done it yet because of political and environmental concerns. If we built nuclear thermal or nuclear pulse propulsion spacecraft, we could reach speeds of a few percent of light speed, maybe 3 to 5%. At 5% of light speed, you could travel about 3 light years in 60 years. That's not quite enough to reach Alpha Centauri at 4.37 light years. You'd need about 87 years for that journey. But you could reach Proxima Centauri at 4.24 light years if you traveled at closer to 5.5% of light speed. At 3% of light speed, you'd only travel about 1.8 light years in 60 years. Not enough to reach any star. So, with nuclear propulsion at realistic speeds of 3 to 5%, you're looking at either needing more than a lifetime for Alpha Centauri, or just barely reaching it if everything goes perfectly and you push to the higher end of speeds. It's borderline. Now, if we look further ahead to technology we might develop in the next 50 to 100 years, the picture improves. With fusion propulsion, if we can solve the engineering challenges, we could reach 10 to 20% of light speed. At 10 to 20% of light speed, you could travel 10 to 20 light years in 60 years. That gives you access to a few dozen star systems. You could visit stars like Alpha Centauri, Sirius, Tau Ceti, Epsilon Eridani, Altair, Procyon. You could explore planets around those stars if they have planets. Some might have habitable worlds, though we don't know yet. The nearest potentially habitable planet we know of, Proxima b, would definitely be within reach. But the vast majority of known potentially habitable exoplanets would remain out of reach. TRAPPIST-1 at 40 light years, unreachable. Kepler 452b at 1,400 light years, impossibly far. So the realistic answer depends on when you're asking. Right now, with current technology, you can't reach any star in a lifetime. With nuclear propulsion, we could build in the next few decades, maybe 1 or 2 stars if you're lucky. With fusion propulsion, we might develop in the next century, 10 to 20 light years, a few dozen stars. That's the honest answer. You'd be limited to a tiny bubble around the Sun. Our galaxy is 100,000 light years across. It contains hundreds of billions of stars. A 20 light-year travel radius gives you access to maybe 100 millionth of the galaxy. The rest, the vast overwhelming majority, would remain forever out of reach, unless you're willing to accept time dilation. If you could travel at 90% of light speed, you could reach stars hundreds of light years away in your lifetime. You could explore thousands of star systems, but you'd lose your connection to Earth. Centuries would pass back home. Everyone you knew would be gone. Your civilization would be transformed beyond recognition. You'd be a visitor from the past, arriving in the distant future. And you could never go home. This is the fundamental trade-off of interstellar travel: distance or time. You can travel far in your own lifetime if you're willing to lose your own time. Or you can stay connected to your own era, but remain confined to a tiny region of space. You can't have both. Not with the laws of physics as we understand them. There's no way to travel faster than light. Now that you know the basic answer, let's talk about why that's the limit and what it would actually take to achieve those speeds. Because understanding the physics is what makes you appreciate both the possibility and the difficulty of interstellar travel. The physical limits imposed by the laws of physics. Because even if we could somehow build engines powerful enough to accelerate a spacecraft to these speeds, we'd run into problems. Serious problems. First, there's energy. Accelerating mass to high speeds requires enormous amounts of energy. The kinetic energy of an object increases with the square of its velocity. Double your speed, and you need 4 times the energy. Triple your speed, and you need 9 times the energy. To accelerate a spacecraft to even 1% of light speed requires staggering amounts of energy. Let's put some numbers to this. Suppose you have a spacecraft with a mass of 100 tons, which is very small for a crewed spacecraft. The International Space Station weighs about 450 tons for comparison, but let's say 100 tons. To accelerate that spacecraft to 1% of light speed, about 6.7 million miles per hour, you'd need an enormous amount of energy. About 1/11,000th of all the electricity the United States uses in a year. And that's just to reach 1% of light speed. To reach 10% of light speed, you need 100 times more energy. About 3% of all the electricity the US uses in a year for one spacecraft. To accelerate to 50% of light speed, you'd need 2,500 times more energy than 1%. Almost as much energy as the entire United States uses in a year, just to accelerate 100 tons to half light speed. And remember, you also have to decelerate when you arrive. So double all those numbers. You need twice as much energy because you have to speed up and then slow down. Where does this energy come from? Chemical rockets, like the ones we use today, are completely inadequate. The chemical energy stored in rocket fuel simply isn't dense enough. The combustion of hydrogen and oxygen, one of the most energetic chemical reactions available, releases about 140 million joules per kilogram of fuel. That sounds like a lot, but it's not. To get 4.5 billion joules from chemical fuel, you'd need about 32 billion kilograms of fuel, 32 million tons. That's more than the mass of the spacecraft by a factor of 320,000. You'd be accelerating mostly fuel, with a tiny spacecraft attached. And that's assuming perfect efficiency, which is impossible. Real rockets lose most of their energy to heat and exhaust that doesn't contribute to thrust. So, in reality, you'd need even more fuel. It's physically impossible with chemical rockets. The mass ratios don't work. You can't build a rocket that's 99.999% fuel. Nuclear propulsion is better. Nuclear reactions release millions of times more energy per kilogram of fuel than chemical reactions. With nuclear fission, you'd need about 56 tons of fuel. That's a mass ratio of about 1.5 to 1. Much more reasonable. You could actually build a spacecraft with that mass ratio. In fact, nuclear propulsion systems have been designed on paper since the 1950s. Project Orion, proposed in the late 50s and early 60s, was a concept for a nuclear pulse propulsion spacecraft. The idea was to drop nuclear bombs out the back of the spacecraft and detonate them. The explosion would hit a pusher plate, a massive shock absorber on the back of the ship, and the force would accelerate the spacecraft forward. Drop another bomb, another push. Repeat thousands of times, and you could reach speeds of a few percent of light speed. The engineering was actually worked out in considerable detail. Simulations showed it could work. Small-scale tests using conventional explosives instead of nuclear bombs demonstrated the concept. But Project Orion was never built. Partly because of the Partial Nuclear Test Ban Treaty in 1963, which banned nuclear explosions in the atmosphere and in space. Partly because of the political and environmental concerns about detonating thousands of nuclear weapons in space. And partly because there was no destination worth reaching. In the 60s, we didn't know about exoplanets. We didn't know if there were any planets around other stars. Building a massive nuclear spacecraft to travel to an empty star system didn't make sense. But the physics worked. Project Orion showed that nuclear pulse propulsion could achieve a few percent of light speed. You could reach Alpha Centauri in about 100 years with Orion. Not quite a single lifetime, but close. 2 or 3 generations. A nuclear thermal rocket is another concept. You use a nuclear reactor to heat a working fluid, usually hydrogen, and expel it out a nozzle. The exhaust velocity is much higher than chemical rockets, up to about 5.6 miles per second compared to 2.8 for chemical. Nuclear thermal rockets were actually built and tested in the 1960s and 70s. The NERVA program, Nuclear Engine for Rocket Vehicle Application, developed and tested several nuclear thermal rocket engines. They worked. They produced thrust. They demonstrated that you could use nuclear fission to heat hydrogen and create a viable rocket engine. But the program was cancelled in 1973 before any engine flew in space. Again, partly because of concerns about nuclear safety and environmental impact. But the technology exists. We could build nuclear thermal rockets today if we wanted to. They could reach speeds of maybe 1 or 2% of light speed with enough fuel. That's about 20 times faster than Parker Solar Probe, but still not fast enough to make interstellar travel quick. You'd still need centuries to reach even nearby stars. To reach 10% of light speed or higher, you'd likely need nuclear fusion. Fusion releases even more energy than fission, about 8 times more energy than fission. With fusion, you'd only need about 7 tons of fuel to reach 1% of light speed. For a 100-ton spacecraft, that's a very manageable mass ratio. And to reach higher speeds, you just need proportionally more fuel. To reach 10% of light speed, you'd need 70 tons of fuel. To reach 20%, 140 tons. These are all feasible mass ratios. You could build spacecraft with these proportions. The problem is, we don't have fusion propulsion yet. We don't even have fusion power plants on Earth. Fusion has been the energy source of the future for the past 70 years, and it still is. We've been working on controlled fusion since the 1950s. we've made enormous progress. We understand the physics much better now than we did decades ago. We've built experimental reactors that achieve fusion reactions and produce energy. The problem is that so far, every fusion reactor we've built consumes more energy than it produces. You have to heat hydrogen to millions of degrees, compress it to incredible densities, and confine it for long enough that the nuclei fuse. This requires enormous amounts of energy input, and the energy output from fusion, while substantial, hasn't yet exceeded the input. We haven't achieved net energy gain. The closest we've come is the National Ignition Facility, NIF, at Lawrence Livermore National Laboratory. In December 2022, NIF achieved fusion ignition for the first time. They used powerful lasers to compress a tiny pellet of hydrogen fuel until it reached fusion conditions. The fusion reaction released more energy than the lasers delivered to the fuel pellet. That's a huge achievement, a genuine breakthrough. But the lasers themselves required about 300 times more energy to operate than the fusion reaction produced. So the overall energy balance was still negative. More energy went into the system than came out. We're making progress, but we're not there yet. Other approaches to fusion include tokamaks, donut-shaped magnetic confinement devices. The ITER project, International Thermonuclear Experimental Reactor, under construction in France, is the largest tokamak ever built. It's designed to achieve net energy gain, producing 10 times more fusion energy than it consumes. But ITER won't be operational until the 2030s at the earliest. And even if ITER succeeds, it's still an experimental reactor, not a working power plant. Converting a successful fusion experiment into a practical power plant will take additional decades. And converting a fusion power plant into a fusion rocket will take even longer. The engineering challenges are different for a rocket. You need to channel the fusion energy into thrust. You need to direct the hot plasma out a nozzle to create propulsion. You need to do this in a compact, lightweight system that can operate in space for years or decades. You need to shield the crew and electronics from the intense radiation produced by fusion reactions. These are all solvable problems in principle, but they haven't been solved yet. So fusion propulsion is theoretically possible, and it would enable travel to 10 or 20% of light speed with reasonable mass ratios. But it's not a technology we have today. It's a technology we might develop in 50 or 100 years if fusion research continues to progress. And even with fusion, reaching the higher speeds, 30, 40, 50% of light speed, becomes extremely challenging. The energy requirements grow with the square of velocity. Remember, to reach 50% of light speed requires 25 times more energy than 10%. Even with fusion's incredible energy density, the fuel requirements become problematic. You'd need 1,750 tons of fusion fuel to accelerate a 100-ton spacecraft to 50% of light speed. That's a mass ratio of 18:1. You'd be burning most of your fuel just to accelerate the rest of the fuel. And again, you need to decelerate when you arrive, so double it. 3,500 tons of fuel for a 100-ton payload. A mass ratio of 36:1. That's getting difficult to engineer. Your fuel tanks would need to be enormous. The structural mass of the tanks themselves would eat into your payload capacity. You'd probably end up with a spacecraft that's 98 or 99% fuel by mass. Possible, maybe, but extremely difficult. A fusion spacecraft designed to reach 50% of light speed would be a massive engineering project. It would require technologies we don't have and probably couldn't build for a century or more. Then there's antimatter. When matter and antimatter meet, they annihilate, converting 100% of their mass into energy. According to Einstein's famous equation, E equals mc squared. This is the most energy-dense fuel theoretically possible. Nothing can release more energy per kilogram than matter-antimatter annihilation. With antimatter, you'd only need about 5 kilograms of fuel to produce the energy needed to reach 1% of light speed. For a 100-ton spacecraft, that's a mass ratio of essentially 1-to-1. Your spacecraft could be almost entirely payload with just a tiny amount of fuel. To reach 50% of light speed, you'd only need about 625 kilograms of antimatter fuel, plus an equal amount of normal matter to annihilate with it, so about 1,250 kilograms total. For a 100-ton spacecraft, that's still very manageable. To reach 90% of light speed, you'd need about 10,000 kilograms, 10 tons of fuel for a 100-ton spacecraft. Still reasonable. Antimatter propulsion would make high-speed interstellar travel genuinely feasible from an energy and mass ratio perspective. The problem, the enormous problem, is that antimatter doesn't exist naturally in any meaningful quantities. You have to create it. And creating antimatter requires enormous amounts of energy. Currently, we can produce tiny amounts of antimatter in particle accelerators. Facilities like CERN in Switzerland can create antiprotons by smashing high-energy protons into targets. Some of the collision energy converts into particle-antiparticle pairs. You can separate out the antiparticles and trap them using electromagnetic fields. But the process is incredibly inefficient. It takes millions of times more energy to create antimatter than you get back when it annihilates. CERN produces about 1/1000th of a gram of antiprotons per year. At that rate, it would take about 10 billion years to produce 1 kilogram. That's longer than the current age of the universe. To produce the amounts of antimatter needed for rocket fuel, we'd need to improve our production efficiency by factors of millions or billions. We'd need dedicated antimatter factories, huge facilities powered by massive energy sources, running continuously for years to produce kilograms of antimatter. No such facilities exist. We have no idea how to build them. The energy requirements would be staggering. You'd need to dedicate a significant fraction of a civilization's entire power output to antimatter production. And even if we solved the production problem, storing antimatter is incredibly difficult. Antimatter annihilates instantly upon contact with normal matter. You can't just put antimatter in a container. The antimatter would touch the walls of the container and annihilate immediately, releasing a burst of energy that would destroy the container and everything around it. The only way to store antimatter is to suspend it in vacuum using electromagnetic fields. Charged particles like antiprotons can be held in place by carefully designed magnetic fields that repel them away from the walls. This is called a penning trap. We can store small numbers of antiparticles in penning traps for days or even weeks. But we've never stored large quantities of antimatter. And the energy required to maintain the electromagnetic fields is substantial. Plus, there's the risk of failure. If the power fails or the magnetic fields fluctuate, or the spacecraft experiences a shock or vibration, the antimatter could touch the walls of its container. The resulting annihilation would be catastrophic. Even a small amount of antimatter, just a few grams, contains enough energy to rival nuclear weapons. A spacecraft carrying tons of antimatter would be essentially a flying bomb. One malfunction, one accident, and the entire ship would vaporize in an explosion brighter than the sun. So antimatter propulsion, while theoretically possible and extremely efficient, faces practical problems that we're nowhere near solving. Producing antimatter in large quantities requires technologies we don't have. Storing it safely requires technologies we don't have. Using it as rocket fuel requires engineering we haven't developed. Maybe someday, centuries from now, we'll solve these problems. Maybe we'll build antimatter factories and develop safe storage systems and design antimatter rockets. But that's not something that's happening in the next few decades. It's speculative technology, far future technology, the kind of thing that might exist in 100 or 200 years if we work very hard on it. So when we talk about realistic propulsion systems, systems we might actually build and use in the foreseeable future, we're limited to nuclear fission and maybe fusion, if we're optimistic. And that limits our speeds to maybe 10 or 20% of light speed, at the very most. Which brings us back to our earlier calculation. 10 to 20% of light speed gets you 10 to 20 light years in 60 years. That's the realistic answer with foreseeable technology. To accelerate to 10% of light speed, you need 100 times more energy than you'd need for 1%. To reach 50% of light speed, you'd need 2,500 times more energy than 1%. The energy requirements grow rapidly and become prohibitive very quickly. Where does this energy come from? Chemical rockets, like the ones we use today, are completely inadequate. The chemical energy stored in rocket fuel simply isn't dense enough. To reach even 1% of light speed using chemical rockets, you'd need more fuel than exists on Earth. It's physically impossible. Nuclear propulsion is better. Nuclear reactions release millions of times more energy per kilogram of fuel than chemical reactions. A nuclear thermal rocket or a nuclear pulse propulsion system, like Project Orion, could theoretically reach speeds of a few percent of light speed. But even nuclear fission has limits. To reach 10% of light speed or higher, you'd likely need nuclear fusion. Fusion releases even more energy than fission and uses lighter elements, like hydrogen, as fuel. A fusion-powered spacecraft could theoretically accelerate to 10 or maybe even 20% of light speed given enough time and fuel. But fusion propulsion is still theoretical. We haven't built a working fusion reactor on Earth yet, let alone a fusion rocket. The engineering challenges are immense. Containing the fusion plasma, channeling the energy into thrust, protecting the spacecraft from radiation. All of these are unsolved problems. Then there's antimatter. When matter and antimatter meet, they annihilate, converting 100% of their mass into energy. According to Einstein's famous equation, E equals mc squared. This is the most energy-dense fuel theoretically possible. An antimatter rocket could theoretically reach speeds approaching a significant fraction of light speed, maybe 30 or 40%, or even higher. But there's a catch. Antimatter doesn't exist naturally in any meaningful quantities. You have to create it, and creating antimatter requires enormous amounts of energy. Currently, we can produce tiny amounts of antimatter in particle accelerators, but it takes millions of times more energy to create antimatter than you get back when it annihilates. We're nowhere near being able to produce antimatter in quantities sufficient for rocket fuel. And even if we solve the production problem, storing antimatter is incredibly difficult because it annihilates instantly upon contact with normal matter. You'd need perfect magnetic or electric field containment, and even the tiniest failure would be catastrophic. So energy is one major limit. But there's another problem. Perhaps even more fundamental, acceleration forces. When a spacecraft accelerates, everyone and everything inside feels a force pushing them backward. This is the same force you feel when a car accelerates or when an airplane takes off. On Earth, we measure this force in multiples of Earth's gravity, called g-forces. 1g is the acceleration you feel standing on Earth's surface. 2g's is twice that, 3g's is 3 times, and so on. Humans can tolerate moderate g-forces for short periods. Fighter pilots experience up to 9g's during tight turns, but only for seconds. Sustained g-forces above 2 or 3g's become uncomfortable and eventually dangerous. Above 5g's sustained for minutes, most people lose consciousness. Above 10g's sustained, you die. Your blood pools, your organs get compressed, your heart can't pump blood to your brain. So if you're accelerating a spacecraft carrying humans, you have to keep the acceleration gentle. Let's say you limit acceleration to 1g. That's the same acceleration you feel on Earth, perfectly comfortable, sustainable, indefinitely. How long does it take to reach 10% of light speed accelerating at 1g? Light speed is about 671 million miles per hour, so 10% is 67 million miles per hour. Accelerating at 1g, which is about 22 miles per hour per second, you gain about 79,200 miles per hour every hour. To reach 67 million miles per hour, you'd need to accelerate for about 846 hours. That's about 35 days. So you could reach 10% of light speed in about a month, accelerating at 1g. That seems reasonable. But here's the problem. You also have to slow down. If you accelerate for 35 days to reach 10% of light speed, you're now screaming through space at 67 million miles per hour. When you reach your destination, you can't just stop instantly. You have to decelerate. And deceleration is just acceleration in the opposite direction. So you'd need another 35 days to slow down. That's 70 days total. About 2.5 months spent just accelerating and decelerating. During that time, you're not traveling at your maximum speed. You're gradually speeding up and then gradually slowing down. Your average speed over those 70 days is only half your maximum speed, about 5% of light speed. This cuts into your travel time significantly. If you're trying to reach Alpha Centauri in 60 years and you spend 70 days accelerating and 70 days decelerating, that's 140 days, about 4.5 months, where you're not at full speed. For a 60-year journey, 4.5 months isn't huge. But for shorter journeys, it matters more. And if you want to reach higher speeds, the acceleration time gets longer. To reach 50% of light speed at 1g acceleration would take about 173 days, nearly 6 months. You'd spend a full year accelerating and decelerating, and that year eats into your travel time. But let's set that aside for now. Let's assume you can accelerate to a reasonable speed, say 10% of light speed, and we'll ignore the time spent accelerating and decelerating. You're cruising at 10% of light speed for most of your 60-year journey. How far can you go? 10% of light speed is about 67 million miles per hour. Over 60 years, that's about 35 trillion miles. That's about 6 light years. You could reach Barnard's star, 6 light years away. You could just barely reach Wolf 359, another nearby star, about 7.8 light years away. But you couldn't quite make it to Sirius at 8.6 light years. And forget about anything farther. Vega, Procyon, Tau Ceti, all unreachable. So with 10% of light speed, which is optimistic given our current technology, a human could reach maybe 2 or 3 nearby star systems in a lifetime. That's it. 2 or 3 stars out of hundreds of billions in our galaxy. But what if we could go faster? What if we pushed to 20% of light speed? At 20% of light speed, 60 years of travel gets you about 12 light years. Now, you can reach Tau Ceti, 11.9 light years away. You can reach Epsilon Eridani, 10.5 light years away. You can reach about a dozen star systems, give or take. 30% of light speed gets you about 18 light years in 60 years. You can reach Altair, 16.7 light years away. You can reach maybe 24 star systems. 50% of light speed gets you about 30 light years. You can reach Vega at 25 light years. You can reach about 50 to 100 star systems, depending on their distribution. You're starting to have options now. Dozens of potential destinations, stars with different characteristics, potentially different planets. But 50% of light speed is hard, really hard. Not just because of the energy requirements, though those are immense. Not just because of the acceleration forces, though those are challenging, but because of relativistic effects. When you travel at speeds approaching the speed of light, Einstein's theory of relativity becomes important. And relativity changes everything. Time dilation occurs. Time passes more slowly for you on the spacecraft than it does for people back on Earth. This isn't some theoretical quirk or mathematical abstraction. This is real, measured, confirmed physics. We've tested time dilation thousands of times in laboratories and in space. Atomic clocks flown on airplanes run slower than identical clocks left on the ground. The difference is tiny, measured in billionths of a second. But it's there, and it matches Einstein's predictions exactly. GPS satellites orbiting Earth have to account for time dilation, or they'd accumulate errors that would make GPS navigation useless within hours. The satellites orbit at about 14,000 miles per hour. At that speed, time on the satellites runs slightly slower than time on Earth because of their velocity. But they're also higher up in Earth's gravitational field, and gravity also affects time. The gravitational time dilation makes time run slightly faster on the satellites than on Earth. These two effects partially cancel out, but there's still a net difference. GPS satellites have to adjust their clocks by about 38 microseconds per day to stay synchronized with Earth time. That's a tiny adjustment, but it's absolutely necessary. Without it, GPS would drift by about 6 miles per day. Within a week, GPS would be useless. So, time dilation is real. It's not speculation. It's physics that we rely on every day. Now, at the speeds we've been discussing, time dilation becomes much more dramatic. The mathematics of time dilation is governed by the Lorentz factor, usually written as gamma. Gamma equals 1 divided by the square root of 1 minus v squared, divided by c squared, where v is your velocity and c is the speed of light. At low speeds, v is much smaller than c, so v squared divided by c squared is close to 0, and gamma is close to 1. Time passes at almost the same rate for you as it does for stationary observers. But as v approaches c, as your speed approaches light speed, the denominator of the Lorentz factor approaches 0, and 1 divided by a number approaching 0 is a number approaching infinity. At light speed, gamma would be infinite. Time would stop completely for you relative to outside observers. You'd age 0 years, while the rest of the universe aged infinitely. But you can't actually reach light speed, so gamma never becomes infinite. It just grows larger and larger as you go faster and faster. At 10% of light speed, time runs about 0.5% slower for you than for Earth. If you experience 60 years of travel time, about 60.3 years pass on Earth. You age 60 years, while Earth ages 60.3 years. The difference is noticeable if you measure it precisely, but it's not dramatic. At 20% of light speed, time runs about 2% slower for you. 60 years, for you, is about 61.2 years on Earth. Still, not a huge difference. At 30% of light speed, time runs about 5% slower for you. 60 years for you is about 63 years on Earth. At 40% of light speed, time runs about 9% slower for you. 60 years for you is about 65.4 years on Earth. At 50% of light speed, time runs about 15.5% slower for you. 60 years for you is about 69.3 years on Earth. The gap is starting to widen, noticeably. At 60% of light speed, time runs about 25% slower for you. 60 years for you is 75 years on Earth. At 70% of light speed, time runs about 40% slower for you. 60 years for you is about 84 years on Earth. Now the difference is significant. People born on Earth when you left would be elderly or gone when you arrived at your destination. A whole generation would have passed. At 80% of light speed, time runs about 67% slower for you. 60 years for you is about 100 years on Earth. You'd return from your journey to find that everyone you knew is gone. Your children, if you had any before leaving, would be old. Your grandchildren would be middle-aged. The world would have changed completely. Technology, politics, culture, all of it would be different. You'd be a visitor from the past, arriving in the future. At 99% of light speed, time slows down dramatically for you. 60 years for you is about 425 years on Earth. Over 4 centuries pass on Earth while you experience a single human lifetime. Everyone you knew is long gone. Multiple generations have come and gone. The civilization you left no longer exists. Languages have evolved. Governments have risen and fallen. Technologies have been invented and made obsolete. You'd arrive on an Earth that's as different from your departure as our world is from the year 1600. Imagine leaving Earth today and arriving back in the era of Galileo, when telescopes were just being invented, when people still debated whether the Earth orbited the Sun, when the scientific method was in its infancy. That's the scale of change you'd experience. At 99.9% of light speed, gamma is about 22.4. 60 years for you is about 1,344 years on Earth. Over a millennium. You'd leave Earth in the 21st century and arrive in the 33rd century. The change would be incomprehensible. You'd have no frame of reference for the world you'd find. At 99.99% of light speed, gamma is about 70.7. 60 years for you is about 4,242 years on Earth, over 4 millennia. You'd leave modern civilization and arrive in a future as far from us as we are from the ancient Egyptians. Imagine trying to explain our world to someone from 2025 BC. Computers, airplanes, nuclear power, quantum mechanics, the internet. None of it would make sense to them. They'd have no conceptual framework to understand it. That's what you'd face, arriving 4,000 years in the future. And this keeps scaling. The closer you get to light speed, the more extreme time dilation becomes. At 99.999% of light speed, time passes at an extremely slow rate for you. 60 years for you is about 13,440 years on Earth. Over 13,000 years. You'd leave the modern world and arrive in a future as distant from us as the end of the last ice age. As you approach arbitrarily close to light speed, time dilation becomes extreme. In principle, you could travel for 60 years and have millions of years pass on Earth. Billions of years, trillions of years. You could leave Earth today and arrive after the sun has died, after the Earth is gone, after the entire solar system is a cold remnant orbiting a white dwarf star. This is both the promise and the horror of relativistic travel. You can travel vast distances in your own lifetime, distances that would take thousands or millions of years at slower speeds can be crossed in decades if you go fast enough. You could visit the center of the galaxy, 26,000 light-years away, in 60 years of your own time. If you traveled at 99.9999% of light speed or so, you could reach Andromeda, 2.5 million light-years away, in 60 years of your own time if you traveled close enough to light speed. You could theoretically travel to the edge of the observable universe in a single human lifetime. But you'd never be able to go home. Not to the home you left. When you arrived at the galactic center after 60 years of your own time, 26,000 years would have passed on Earth. Human civilization, as we know it, wouldn't exist anymore. Our species might not exist anymore. Earth might be uninhabitable. The sun might have evolved into a different stage of its life. Everything you knew would be gone, erased by the passage of time. When you arrived at Andromeda after 60 years of your own time, 2.5 million years would have passed on Earth. Our species, Homo sapiens, is only about 300,000 years old. 2.5 million years is longer than our species has existed. By the time you arrived at Andromeda, humanity might have evolved into a completely different species, or gone extinct, or colonized the galaxy and become unrecognizably advanced. You'd have no idea what you'd find when you tried to send a message back to Earth. Earth might not even be there anymore. And if you traveled to the edge of the observable universe, tens of billions of years would pass on Earth. The sun would long since have died. It would have swollen into a red giant about 5 billion years from now, engulfing Mercury and Venus, and possibly Earth. Then it would have shed its outer layers and collapsed into a white dwarf, slowly cooling over billions of years. By the time you reached the edge of the observable universe and looked back toward where Earth used to be, the white dwarf remnant of our sun would be cold and dark, just a dead cinder floating in space. The Earth, if it survived the red giant phase, would be a frozen wasteland orbiting a dead star. No life, no atmosphere, no warmth. Just a ball of rock in eternal darkness. That's what time dilation means. You can cheat distance, but you can't cheat time. You can travel far, but only by abandoning your own era and arriving in a future you'll never recognize. This is one of the profound philosophical implications of relativity. It means that interstellar travel at high speeds is fundamentally a one-way journey through time. You can go, but you can't come back. Not to the time you left. You can physically return to Earth, sure. You can turn your spacecraft around and fly back. But when you arrive, it won't be the Earth you remember. It will be Earth in the future. Centuries or millennia or millions of years in the future, depending on how fast you traveled and how far you went. Everyone you knew will be gone. Everything you cared about will be gone. You'll be a stranger in a strange land, a relic from the past visiting a future you can't comprehend. Some people might embrace this. Some people might see it as an opportunity to explore the far future, to witness the evolution of humanity and civilization across vast timescales, to see what becomes of our species, what we achieve, where we go. But most people wouldn't. Most people want to stay connected to their own time, to the people they know, to the world they understand. Most people wouldn't trade 60 years with their families and friends for the chance to visit distant galaxies and arrive in a future where everyone they loved is dust. The cost is too high. So relativistic travel solves the distance problem, but creates a time problem that's equally severe. And for most practical purposes, for the kind of interstellar travel we might actually attempt in the next few centuries, we're limited to speeds where time dilation is modest, where the difference between Earth time and ship time is years or decades, not centuries or millennia, which means speeds of maybe 10, 20, at most 30 or 40% of light speed, enough to reach nearby stars in a lifetime, not enough to reach distant galaxies. This is real. This is actual physics, confirmed by countless experiments. Atomic clocks, flown on airplanes, tick slower than clocks on the ground. Particles accelerated to high speeds in accelerators live longer than stationary particles. Time dilation is fact. So if you could somehow travel at 99% of light speed for 60 years of your own time, you'd cover about 58.4 light years. You could reach hundreds of star systems. Deneb, Antares, Betelgeuse, all within range. But when you arrived, over 400 years would have passed on Earth. Everyone you knew would be dead. The civilization you left would be gone, transformed into something unrecognizable. You'd be a time traveler, arriving in the future, unable to return to your own time. This is one of the profound implications of near-light speed travel. You could travel far, farther than any ship limited by the ticking of Earth's clock. But you'd lose your connection to home. You'd become unstuck from your own era. At extreme speeds, time dilation becomes even more dramatic. At 99.9% of light speed, 60 years for you is over 1,340 years on Earth. You'd travel about 59.9 light years. At 99.99% of light speed, 60 years for you is over 4,240 years on Earth. You'd travel about 59.99 light years. As you approach closer and closer to light speed, you can travel farther and farther in your own lifetime, while millennia pass on Earth. The ultimate limit is the speed of light itself. According to Einstein's special relativity, nothing with mass can reach the speed of light. As you accelerate closer to light speed, your mass increases, your length contracts, and time slows down. It would take infinite energy to accelerate to exactly light speed. Light itself travels at light speed because photons have no mass. Anything with mass is forever limited to speeds below light speed. So in principle, if you had unlimited energy and could accelerate to 99.99999% of light speed, arbitrarily close, but never quite reaching it, you could travel arbitrarily far in your own lifetime. You could cross the entire galaxy, 100,000 light-years, in 60 years of your own time. But tens of thousands of years would pass on Earth. You could reach the Andromeda Galaxy, 2.5 million light-years away, in 60 years of your own time. But millions of years would pass on Earth. You could theoretically travel to the edge of the observable universe in a single human lifetime if you traveled close enough to light speed. But by the time you arrived, everyone and everything you knew would be gone. The Earth might not even exist anymore. The sun would have exhausted its fuel and died. Humanity, if it survived at all, would be unrecognizably different. You'd arrive in a future so distant that nothing remains of your origin except perhaps archaeological records or legends. This is the paradox of near-light-speed travel. It makes vast distances crossable in a human lifetime, but only by severing all connection to the time you came from. You can go far, but you can never go home. Not to the home you left, anyway. Now let's step back and consider realistic scenarios. What could we actually build in the next few decades? Not theoretical spacecraft powered by antimatter or traveling at 99% of light speed. Actual engineering projects with technologies we understand or could plausibly develop. The most ambitious, realistic design currently being worked on is Breakthrough Starshot. This is a real project, not science fiction. It was announced in 2016, funded by investors including Yuri Milner and Mark Zuckerberg, and supported by the late Stephen Hawking. The stated goal is to send a probe to Alpha Centauri within a generation. The idea is elegant in its simplicity. Build thousands of tiny spacecraft, each weighing only a few grams. Essentially, computer chips with cameras and transmitters attached. Attach a light sail to each one, a thin reflective material just atoms thick. Then, use powerful lasers based on Earth to push on these light sails. Light carries momentum. When photons hit a surface and reflect, they transfer momentum to that surface. It's an incredibly tiny force for individual photons, but with enough photons, with powerful enough lasers, you can generate measurable thrust. And because the spacecraft is so light, just a few grams, even tiny thrust can produce significant acceleration. The proposal calls for building a laser array in a high-altitude desert location, probably in Chile. This array would consist of thousands of individual laser modules, each producing kilowatts or megawatts of power. Combined, they'd generate perhaps 100 gigawatts of laser power. That's about 100 times the power output of a large nuclear power plant. All of this laser energy would be focused into a tight beam and aimed at the light sail. For the first few minutes of flight, while the spacecraft is relatively close to Earth, the laser would push on the sail, accelerating it. The acceleration would be enormous. Calculations suggest accelerations of about 30,000 Gs. That's 30,000 times Earth's gravity. No human could survive it. No delicate instruments could survive it. But a simple computer chip embedded in a solid block could survive. It's just a piece of electronics. No moving parts, nothing fragile. It can handle the acceleration. After a few minutes of this intense acceleration, the spacecraft would reach about 20% of light speed. At that point, it would be too far away for the laser to push it anymore. The laser beam would have spread out too much. Most of the photons would miss the sail. So the acceleration would stop, and the spacecraft would coast the rest of the way to Alpha Centauri at 20% of light speed. The journey would take about 20 years. When the spacecraft reached Alpha Centauri, it would fly past at 20% of light speed. No slowing down, no stopping. moving too fast for any known propulsion system to decelerate. It would have just a few hours to take pictures and gather data as it screamed through the system. Then it would beam that data back to Earth using a small laser. The data would take 4.24 years to reach us, traveling at light speed. So about 24 years after launch, we'd receive pictures and scientific data from Alpha Centauri. That's the plan. It's ambitious, but it's not impossible. The physics works. Light sails have been tested in space. Japan's Ikaros spacecraft, launched in 2010, successfully demonstrated solar sail propulsion. It used sunlight instead of lasers, but the principle is the same. The main challenges are engineering challenges. Building lasers powerful enough. Building light sails thin enough and large enough. Focusing the laser beam precisely enough to hit a meter-sized target that's moving away at relativistic speeds. Protecting the sail from being vaporized by the intense laser energy. Building electronics that can survive the acceleration and the radiation of interstellar space. These are all hard problems, but they're not physics problems. They're engineering problems. And engineering problems can be solved with enough time, money, and effort. Breakthrough Starshot has been working on these problems since 2016. Progress has been slow. The project is still in the research phase, studying materials, designing laser systems, running simulations. No hardware has been built yet. No actual light sail spacecraft have been constructed. The laser array hasn't been started. Optimistic estimates suggest the first launch might happen in the 2040s or 2050s. More conservative estimates push it to the second half of the century or beyond. But the point is that it's possible. Within the next 50 years, we could send a probe to another star, not a human, just a tiny robotic probe weighing a few grams. But it would be the first human-made object to reach another star system in less than a human lifetime. That's a genuine milestone. However, here's the critical limitation. These are tiny probes. A few grams. They can't carry humans. They're barely large enough to carry a camera and a transmitter. They're designed for a one-way flyby mission. Take pictures, send data, done. No landing, no exploring, no sample return. Certainly no carrying humans. To build a spacecraft large enough to carry a human, you'd need something vastly bigger. A spacecraft with life support, radiation shielding, food, water, air recycling, waste management, living quarters, exercise equipment to prevent muscle loss in zero gravity, medical supplies, communication systems, navigation, power generation. All the infrastructure needed to keep a human alive for decades in the harsh environment of deep space. You're talking about a spacecraft weighing tons, not grams, possibly hundreds of tons for a crewed interstellar mission. And accelerating tons to 20% of light speed is vastly harder than accelerating grams. The energy requirements scale linearly with mass. A spacecraft 1,000,000 times heavier needs 1,000,000 times more energy to reach the same speed. If it takes 100 gigawatts of laser power for a few grams, it would take roughly 10 to the 17 watts, 100,000 trillion watts, to accelerate 100 tons. That's about 100,000 times all the power humanity currently generates worldwide. It's absurd, completely impractical. And even if you could somehow generate that much power, there's another problem. Laser intensity drops with distance according to the inverse square law. Double the distance and the intensity drops to 1/4. Triple the distance and it drops to 1/9. By the time the laser beam reaches a spacecraft that's even a few light seconds away, It's spread out over a huge area. The beam divergence means most of the energy misses the sail. You can reduce beam divergence by using larger laser apertures or shorter wavelengths, but there are limits. Diffraction is a fundamental property of light waves. You can't eliminate it completely. To keep a laser beam focused on a target that's light minutes or light hours away requires apertures miles across or wavelengths in the X-ray range, neither of which is practical with current technology. So the laser pushing concept works for very small spacecraft that only need to be accelerated over short distances while they're relatively close to Earth. But it doesn't scale up to human-carrying spacecraft. The physics doesn't allow it. Another concept is the generation ship. Instead of trying to travel fast enough to reach another star in one person's lifetime, you build a ship large enough to support a population of people for many generations. The ship travels at a slower speed, maybe 1% or 5% of light speed. Achievable with nuclear propulsion, the journey takes centuries. The people who start the journey aren't the ones who finish it. Their children continue the mission. Then, their grandchildren. Then their great-grandchildren, generation after generation living on the ship, maintaining it, operating it, moving slowly toward a distant star. Eventually, after 10 or 20 or 50 generations, depending on the distance and speed, the ship arrives at its destination. The people who step off the ship onto a new world have never seen Earth. They were born on the ship. Their parents were born on the ship. Their grandparents and great-grandparents were born on the ship. Earth is just a story to them, a myth, the place their distant ancestors came from. They've spent their entire lives in the artificial environment of the ship. Everything they know, everyone they've ever met, every experience they've had, all of it has been within the metal walls of the generation ship. And now they're arriving at a new world, a real planet with open skies and natural gravity and an ecosystem. It would be overwhelming. Like someone who's lived their entire life in a small town, suddenly dropped into the middle of a vast wilderness. Generation ships solve the distance problem by removing the lifetime constraint. You don't need to reach the destination in one lifetime if you're willing to commit multiple lifetimes to the journey. The mission becomes multi-generational, a project that spans centuries. But generation ships have their own massive problems. First, population, genetics. You need a ship large enough to support a stable population. Too few people and genetic diversity becomes a problem. Inbreeding increases the risk of genetic disorders. Harmful recessive genes that are rare in large populations become common in small, isolated populations. The effects compound over generations. By the time the ship reaches its destination, the population could be suffering from serious genetic problems, reduced fertility, increased disease susceptibility, shorter lifespans, cognitive impairments. This is a real concern. Studies of isolated human populations throughout history show that populations smaller than a few hundred individuals tend to experience genetic bottlenecks. For a generation ship that will be isolated for centuries, you'd probably need at least 500 to 1,000 individuals to maintain genetic health. Some studies suggest even more, perhaps several thousand. And these aren't just passengers sitting in suspended animation. These are active, living, breeding populations. You need children to replace people as they die. You need enough genetic diversity that people can find mates who aren't closely related. You need social structures to manage reproduction and prevent inbreeding. This means a generation ship would need to be enormous, housing thousands of people requires vast amounts of space. Living quarters, common areas, workspaces, agricultural areas to grow food, water recycling systems, waste treatment, power generation, maintenance shops, medical facilities, schools, recreation areas. You're basically building a small city that can survive indefinitely in space with no resupply. The Stanford Torus, a design proposed in the 1970s, is one example of what this might look like. It's a rotating ring, about 1.1 miles in diameter. The rotation creates artificial gravity through centrifugal force. People live on the inner surface of the ring, walking on the inside of the torus. It would house about 10,000 people. The structure would be massive. Millions of tons of material. And it's just the habitat. You'd still need propulsion systems to accelerate it to a few percent of light speed and decelerate it at the destination. You'd need power systems to run it for centuries. You'd need shielding to protect against cosmic radiation. The engineering would be staggering. Then there's life support. A generation ship needs closed-loop life support. Everything has to be recycled. Air, water, waste, nutrients, all of it. Nothing can be resupplied from Earth. The ship has to be entirely self-sufficient for hundreds of years. We've never built a closed life support system that can operate without external inputs for that long. The International Space Station recycles water and air, but it still requires regular resupply missions from Earth. Food, spare parts, equipment, all shipped up from Earth every few months. A generation ship wouldn't have that option. It would need to produce all its own food through agriculture, grow plants, raise animals potentially, harvest and process everything on board. The plants would need to produce enough oxygen to breathe and enough biomass to eat. The waste products, carbon dioxide, urine, feces, dead plant matter, would need to be broken down and recycled back into nutrients for the plants. The loop would need to be almost perfectly closed. Any leakage, any inefficiency in recycling would compound over centuries and eventually exhaust the ship's resources. Even a 1% loss per cycle, which sounds small, would be catastrophic over hundreds of years. No ecosystem on Earth operates as a perfectly closed loop. There's always exchange with the environment, always inputs and outputs. Can we build a truly closed artificial ecosystem that operates for centuries without failure? We don't know. We've attempted small-scale closed ecosystem experiments. Biosphere 2, built in Arizona in the early 1990s, was an attempt to create a sealed ecosystem. 8 people lived inside for 2 years, growing their own food, recycling air and water. It didn't go well. Oxygen levels dropped. Carbon dioxide levels rose. Food production was insufficient. The crew lost weight. They had to import oxygen and food. The experiment showed how difficult it is to maintain a balanced, closed ecosystem, even for a small number of people for a short time. Scaling that up to thousands of people for centuries is a daunting challenge. Then there's the social stability problem. People living their entire lives on a ship, knowing they'll never reach the destination. Knowing only their distant descendants will benefit from the mission. That requires incredible commitment. A sense of purpose that spans generations. What happens if people lose faith in the mission? What if a generation decides they don't want to continue toward a star they'll never see? What if they want to turn around and go back to Earth? Or stop at some intermediate point and build a colony somewhere else? What if there's conflict between generations about the mission's goals? What if social structures break down? What if there's violence, civil war, sabotage? These aren't just hypothetical concerns. Human societies throughout history have experienced internal conflicts, revolutions, collapses. Civilizations that seemed stable for centuries have fallen apart within generations. And those civilizations had the entire Earth to work with. Resources, space, options. A generation ship would have none of that. It would be a tiny, isolated population locked in a metal container in the void of space. If social cohesion breaks down, if people start fighting, there's nowhere to go. No escape, no external help, no hope of rescue. The mission could fail, not because of technical problems, but because of human problems. And history suggests that's a real risk. Maintaining social stability for centuries in an isolated population would require careful governance, cultural continuity, education, a shared sense of purpose. It would require people to believe in a mission they'll never see completed, to make sacrifices for descendants they'll never meet. That's asking a lot, maybe too much. Then there's propulsion. Even at 1% of light speed, a generation ship needs massive amounts of energy. If the ship weighs thousands or tens of thousands of tons, accelerating it to 1% of light speed and then decelerating it again requires fuel. Lots of fuel. Chemical propulsion is completely inadequate, as we've discussed. Nuclear fission could work, but you'd need a huge reactor and a lot of uranium or plutonium. The ship would be radioactive. You'd need heavy shielding to protect the crew from radiation. That adds even more mass. Nuclear fusion would be better, but we don't have fusion propulsion yet. One interesting concept is the Bussard ramjet, proposed by physicist Robert Bussard in 1960. The idea is to scoop up hydrogen from space as you travel. Interstellar space isn't empty. It contains about 1 hydrogen atom per cubic centimeter on average. That's incredibly sparse, but if you're moving fast enough and your scoop is large enough, you can collect significant amounts of hydrogen. Then you use that hydrogen as fuel for fusion reactions. The energy from fusion powers the ship, accelerating it further. As you go faster, you collect more hydrogen per second because you're sweeping through space faster. More hydrogen means more fusion. Power means more thrust, means more acceleration. In principle, a Bussard ramjet could continuously accelerate, reaching higher and higher speeds without carrying fuel. The fuel is collected from space itself. It's a beautiful concept. But there are problems. First, you need a scoop to collect the hydrogen. To collect enough hydrogen at reasonable speeds, the scoop needs to be enormous, thousands of miles across. You'd use magnetic fields to funnel hydrogen into the collector. But generating magnetic fields that large and that strong requires huge amounts of power. More power than the fusion reactions might produce, especially at low speeds. You'd need an enormous initial power source just to get the ramjet started. Second, even if you can collect the hydrogen, fusing it is hard. The hydrogen in interstellar space is mostly regular hydrogen, not deuterium or tritium. Fusing regular hydrogen requires higher temperatures and densities than fusing deuterium. We've never achieved sustained hydrogen fusion in a reactor. We can barely achieve deuterium fusion, and that's with enormous experimental facilities on Earth. Third, even if you can fuse the hydrogen, using it efficiently for propulsion is another challenge. The fusion products need to be directed out the back of the ship to create thrust. That requires complex magnetic nozzles and plasma handling systems. All of this is theoretical. No Bussard ramjet has ever been built. It's an idea on paper, a concept that might work if we solve multiple unsolved problems in fusion physics, plasma dynamics, and magnetic field engineering. It's not something we could build in the next few decades. Maybe not in the next century. So generation ships are theoretically possible, but practically very difficult. They require technologies we don't have, social structures we've never tested, and a level of commitment and faith in the future that may be beyond what humans are willing to sustain. They're a possible solution to interstellar travel, but not an easy one. Another option is suspended animation or cryogenic freezing. If you could freeze a human being, stop all biological processes, and then thaw them out decades or centuries later, without damage, you could extend the effective lifetime of the traveler. A person could be frozen for the duration of a centuries-long journey and wake up at the destination, biologically, the same age they were when they left. This would allow slow-speed travel without requiring generation ships. You wouldn't need a huge population. You could send a small crew, maybe a few dozen people, frozen in cryogenic pods. The spacecraft could be much smaller because you wouldn't need living quarters, food production, extensive life support for active humans. Just a power source to maintain the freezing systems and enough shielding to protect the frozen crew from radiation. The ship could travel at modest speeds, 1 or 2% of light speed, taking centuries to reach its destination. When it arrived, automated systems would wake the crew. They'd step off the ship, stretch their muscles, and begin exploring a new world. To them, the journey would feel like a single night's sleep. They'd close their eyes on Earth and open them orbiting an alien star. Decades or centuries would have passed, but they wouldn't have aged a day. It's an elegant solution to the time problem. But we don't have this technology, not even close. We can freeze cells. Individual cells, small clumps of cells, can be frozen and revived. This is routinely done with sperm, eggs, embryos for fertility treatments. Frozen sperm can remain viable for decades. Frozen embryos have been successfully implanted and grown into healthy babies years after freezing. We can freeze tissues, small pieces of organ tissue for research. We can even freeze some small organisms and revive them. Certain types of frogs can survive being frozen solid in winter. Their bodies produce antifreeze compounds that prevent ice crystal formation in their cells. In spring, they thaw out and hop away. Tardigrades, microscopic animals, can survive being frozen to near absolute zero. They enter a state called cryptobiosis, where their metabolism drops to almost nothing. Years later, add water and warmth, and they come back to life. But these are small organisms with simple body structures. Freezing a whole human being, with a complex brain containing 100 billion neurons and 100 trillion connections, is vastly harder. The main problem is ice. When water freezes, it forms crystals. Ice crystals have sharp edges. As they grow, they puncture cell membranes, tear apart tissues, damage proteins. A frozen cell is a dead cell in most cases. When you freeze a piece of meat in your freezer, ice crystals form in the muscle tissue. When you thaw it, the texture changes. It becomes mushy because the ice crystals have destroyed the cellular structure. The same thing happens with human tissue. Freeze a human, and ice crystals will form in every cell in the body. Brain cells, heart cells, liver cells, all damaged by ice. When you thaw the body, you don't get a living person. You get a corpse with ice-damaged organs and a destroyed brain. We've known this for decades. But We've also developed methods to reduce ice crystal formation. Cryoprotectants are chemicals that lower the freezing point of water and interfere with ice crystal growth. Glycerol, DMSO, ethylene glycol. These are common cryoprotectants. They replace some of the water in cells and prevent large ice crystals from forming. With cryoprotectants, you can freeze tissue and minimize ice damage. Organ transplants sometimes use this technique. A donated organ can be treated with cryoprotectants and cooled to sub-zero temperatures for longer preservation. When it's needed, it's warmed up and transplanted. Success rates vary, but it works for some organs for short periods. The problem is getting cryoprotectants distributed evenly throughout a whole body. For a small tissue sample, you can immerse it in cryoprotectant solution. The chemicals diffuse through the tissue relatively quickly. But for an entire human body, you'd need to perfuse the cryoprotectants through the circulatory system. Pump them through the blood vessels so they reach every cell. This is technically possible. Alcor and other cryonics organizations do this with people who've chosen to be cryopreserved after death. Within minutes of legal death, they start perfusion. They pump out the blood and replace it with cryoprotectant solution. Then they cool the body slowly to liquid nitrogen temperature, minus 196 degrees Celsius. At that temperature, all biological processes stop. Decay stops. The body can theoretically be stored indefinitely. The hope is that future technology will be able to reverse the freezing process, repair any damage, and revive the person. It's speculative, but it's based on the idea that if the brain structure is preserved, if the neural connections that encode memories and personality are intact, then in principle, a sufficiently advanced technology could restore function. But here's the critical problem. The people being cryopreserved are already gone. They died of disease, or old age, or injury. Their brains were already damaged before freezing. They've been without oxygen for minutes or hours. Neural tissue is extremely sensitive to oxygen deprivation. After about 5 minutes without oxygen, brain cells start dying. After 10 or 15 minutes, massive, irreversible damage occurs. Even if you could perfectly preserve a brain that's been gone for an hour, you're preserving a brain that's already heavily damaged. Could future technology repair that damage? Maybe. We don't know. But we do know that the freezing process itself causes additional damage. Even with cryoprotectants, some ice formation occurs. Some cells rupture. Some proteins denature from the cold. When you thaw the tissue, it's not the same as before freezing. There's damage, maybe subtle, maybe extensive. For cryonics to work as a path to future revival, 2 things need to be true. First, the freezing and preservation process needs to maintain enough brain structure that memories and personality could theoretically be reconstructed. Second, future technology needs to be capable of repairing the damage caused by both the original cause of death and the freezing process. Both of these are uncertain. We don't know how much damage is too much for revival. We don't know what future technology will be capable of. It's a gamble based on hope and speculation. But what we're talking about for interstellar travel is different. We're not talking about freezing people after death. We're talking about freezing healthy living people and reviving them later, still healthy and alive. That's never been done. We've never successfully frozen and revived a mammal. We've tried. Experiments in the 1950s and 60s attempted to freeze dogs and cats, cool them to sub-zero temperatures, then warm them up. The animals died. Ice damage was too severe. Hearts wouldn't beat. Lungs wouldn't breathe. Brains showed no activity. More recent experiments have achieved limited success with small mammals. Researchers have cooled rats to near freezing, stopped their hearts, kept them in a state of deep hypothermia for hours, then warmed them up and revived them. But this isn't true freezing. The body temperature drops to just above freezing, close to 0 degrees Celsius, but not below. No ice forms. It's suspended animation, not cryopreservation, and it only works for hours, not years or decades. True cryopreservation, freezing to liquid nitrogen temperature and holding for extended periods, has never been successfully reversed in a mammal. The technology doesn't exist. We don't know if it's possible. Maybe the damage from ice formation is fundamentally irreversible. Maybe there's no way to freeze a brain and preserve all the delicate structures that encode memory and consciousness. Maybe freezing necessarily destroys something essential, some aspect of brain function that can't be restored. Or maybe it's just an engineering problem we haven't solved yet. Maybe with better cryoprotectants, better freezing protocols, better rewarming techniques, better repair mechanisms, we could make it work someday. So where does this leave us for interstellar travel? Cryogenic freezing or suspended animation would be transformative if we had it. It would eliminate the generation ship problem. It would allow slow-speed travel without requiring people to live and die en route. It would make interstellar colonization vastly easier. But we don't have it. We're nowhere close to having it. It might be developed in the next century. It might never be developed. We don't know. For the foreseeable future, for the missions we might actually attempt in the next 50 to 100 years, we can't rely on cryogenic freezing. We have to assume people will be awake and alive for the entire journey. Which brings us back to the fundamental constraint. A human lifetime is about 60 years of active travel time. That's what we have to work with. So where does this leave us? What's the realistic answer to our original question? How far can a human actually travel through space in one lifetime using technology we have or might develop soon? The answer depends on what you mean by soon. With current technology, chemical rockets and ion drives, a human couldn't reach another star in a lifetime. We could send probes to the outer solar system. We could maybe reach the heliopause, the edge of the sun's influence. But interstellar space, the space between stars, would remain out of reach. With nuclear propulsion, which might be developed in the next few decades, we could potentially reach a few % of light speed. At 5% of light speed, you could reach Alpha Centauri in about 87 years. Too long for a single lifetime, unless you left very young and lived very long. But you could reach nearby stars within a few light years in a lifetime. Barnard's star, Wolf 359, maybe Sirius if you're lucky. A handful of destinations. With fusion propulsion, which might be developed in the next century if we solve the engineering challenges, we could reach 10 or 20% of light speed. At 20% of light speed, you could reach Alpha Centauri in about 22 years. You could visit several star systems in a lifetime. You could explore a small neighborhood around the sun. Dozens of stars, possibly hundreds, if you travel efficiently and use gravitational assists. With antimatter propulsion, which is far more speculative and might never be practical, you could reach 30, 40, maybe 50% of light speed. At 50% of light speed, you could reach stars 30 light-years away in 60 years. You could visit hundreds of star systems. You could explore a significant volume of space around the Sun. But antimatter propulsion requires solving problems we're nowhere near solving, producing antimatter in large quantities, storing it safely, using it efficiently. These are challenges that might take centuries to overcome, if they're solvable at all. But there's another set of problems we haven't discussed yet. Problems that affect any interstellar journey, regardless of propulsion system. The hazards of traveling through interstellar space at high speed. Space isn't empty. We think of it as a perfect vacuum, but it's not. Interstellar space contains about 1 atom per cubic centimeter on average. That sounds incredibly sparse, and it is. A cubic centimeter is about the size of a sugar cube. 1 atom per sugar cube volume is almost nothing. For comparison, air at sea level contains about 25 billion trillion atoms per cubic centimeter. So, interstellar space is 25 billion trillion times less dense than air. It's as close to a perfect vacuum as you can get. But when you're traveling at 10 or 20% of light speed, even that sparse density becomes a problem. When you're moving at 60 million miles per hour, you're sweeping through billions of cubic centimeters of space per second. Each atom you encounter hits your spacecraft with significant energy. The kinetic energy depends on your velocity. At 10% of light speed, each hydrogen atom hits with about half an electron volt of energy. That's tiny. 1 electron volt is the energy an electron gains when accelerated through 1 volt of electric potential. It's an incredibly small amount of energy. But you're hitting billions of atoms per second. And those impacts add up. Over years of travel, the cumulative bombardment is significant. The front of your spacecraft becomes essentially a target in a shooting gallery. Trillions upon trillions of atoms smashing into it continuously. Each impact deposits energy. The material heats up. At higher speeds, the problem gets worse. At 50% of light speed, each atom carries about 12 electron volts of energy. That's 25 times more energy per atom than at 10%. At 90% of light speed, each atom carries over 400 electron volts, over 800 times more than at 10%. The heating becomes severe. The front surface of your spacecraft could reach temperatures hot enough to glow red, then white hot. You'd need cooling systems to dissipate this heat, radiators to dump the thermal energy into space, and you'd need shielding to protect the rest of the spacecraft and the crew from this bombardment. Then there's the problem of larger particles. Interstellar space doesn't just contain individual atoms, it also contains dust grains. Tiny particles of ice, rock, carbon, ranging from nanometers to micrometers in size. There aren't many of them, maybe 1 dust grain per few cubic miles on average. But when you're traveling at relativistic speeds across light years, you'll encounter them. A dust grain, a micrometer across, weighs about 1 trillionth of a gram. Tiny. But at 10% of light speed, it carries about 10,000 joules of kinetic energy. That's roughly the energy of a bullet fired from a handgun. A single dust grain hitting your spacecraft at 10% of light speed has the same impact as being shot with a gun. At 50% of light speed, the same dust grain carries 250,000 joules. Like being hit with a high-powered rifle round. At 90% of light speed, over 8 million joules, equivalent to several kilograms of TNT exploding. A single microscopic dust grain. If it hits your spacecraft, it punches through the hull, creates a hole, damages systems, possibly kills crew members if it penetrates the living areas. And you can't avoid them. You can't see them coming. A dust grain is too small to detect from a distance with any instrument we have. By the time you know it's there, it's already hit you. You need shielding. Thick shielding on the front of your spacecraft to absorb the impacts. But shielding adds mass. More mass means more fuel needed for acceleration and deceleration. More fuel means a heavier spacecraft. The engineering becomes difficult very quickly. Some designs propose using a sacrificial shield, a thick plate of material positioned ahead of the main spacecraft. When a dust grain hits the shield, it vaporizes both the grain and a small amount of the shield material. The resulting plasma expands and disperses. By the time it reaches the main spacecraft behind the shield, it's spread out over a large area. The energy per unit area is much lower, easier to handle. The spacecraft can survive. But the shield gradually erodes from these impacts. Over years of travel, it gets thinner and thinner. You need to start with a very thick shield to ensure it lasts the entire journey. Again, more mass. Another hazard is radiation. Space is filled with radiation, cosmic rays, high-energy particles from exploding stars and other energetic events throughout the galaxy. They're mostly protons, hydrogen nuclei, traveling at close to light speed. When they hit matter, they can penetrate deep inside, damaging cells, breaking DNA, causing cancer. On Earth, we're protected by the atmosphere and the magnetic field. The atmosphere absorbs most cosmic rays before they reach the surface. The magnetic field deflects many of them away from Earth entirely. But in deep space, there's no atmosphere, no magnetic field. Astronauts on the International Space Station receive about 150 times more radiation than people on Earth's surface. And they're still relatively close to Earth, within its magnetosphere, with some protection. Astronauts on deep space missions, traveling to Mars, for instance, would receive even higher radiation doses. For a journey to another star lasting decades, the cumulative radiation exposure would be enormous, enough to significantly increase cancer risk, possibly enough to cause radiation sickness during the journey. You need shielding. But shielding radiation is hard. You need thick barriers of material, meters of water or metal or specialized shielding compounds. All of it adds mass. Some designs propose using water as shielding. Water is effective at absorbing radiation, and you need water anyway, for drinking, growing food, producing oxygen. So you arrange the water tanks around the living quarters. The water serves double duty, life support and radiation shielding. But you still need a lot of it. Meters of water all around the crew compartment. Thousands of tons for a reasonably sized habitat. And that's just for radiation from cosmic rays. If the sun has a solar flare while you're still in the solar system, the radiation spike could be deadly without adequate shielding. Then there's the psychological challenge, spending 60 years confined to a small spacecraft. You can't go outside. There's no outside to go to, just the vacuum of space and deadly radiation. You're stuck inside a metal container, the same walls, the same rooms, the same recycled air for decades. On Earth, even in the most remote locations, you can step outside. You can see the horizon. You can feel wind, see weather, experience natural light. On a spacecraft, none of that exists. You have artificial lighting, recycled atmosphere, the constant hum of machinery. No seasons, no day-night cycle beyond what's artificially created. no natural environment at all. Studies of isolated groups, Antarctic research stations, submarines, space stations, show that people struggle with long-term confinement. Depression, anxiety, interpersonal conflicts all become more common. The Antarctic research stations, where people spend months in isolation during the winter, when it's too dangerous to leave or receive supplies, have documented numerous psychological issues. People become irritable, withdrawn, sometimes hostile. Conflicts arise over trivial matters. The isolation and monotony wear people down, and those are only months, not decades. And the people can still communicate with the outside world. They can email, video call, know that rescue is possible if something goes terribly wrong. On an interstellar spacecraft, you can't. Communication with Earth gets slower as you get farther away. At 1 light-year distance, messages take 1 year to reach Earth and another year for a reply to come back. 2-year round trip. At 10 light years, 20-year round trip. You ask a question and you might be middle-aged by the time you get an answer. The conversations become asynchronous letters to the future. You're sending messages to people who might not even be alive when your message arrives. And there's no rescue. If something breaks, if someone gets sick, if the mission fails, you can't call for help. Help is years or decades away. By the time a rescue mission could be organized and sent, you'd be long gone. You're completely on your own. Psychological support would be critical. Counselors, therapists, activities to keep people mentally healthy, art, music, virtual reality simulations of Earth, anything to provide mental stimulation and emotional connection. But it's uncertain whether that would be enough. We've never tried to keep people psychologically healthy in isolation for 60 years. We don't know if it's possible. Maybe the human mind isn't built for that kind of confinement. Maybe we need real horizons, real nature, real connection to Earth to stay sane. Maybe after a few decades, even the strongest minds would break down. Or maybe humans are more resilient than we think. Maybe with the right environment, the right support systems, the right sense of purpose, people could handle it. We don't know. We won't know until we try. And that's a risk. You're asking people to volunteer for a mission that might psychologically destroy them, that might leave them damaged, broken, unable to function by the time they reach their destination. Is that ethical? Is it worth it? These are questions without easy answers. So, when we talk about how far a human can travel in a lifetime, we're not just talking about physics and engineering. We're also talking about biology, psychology, sociology. Can the human body survive decades in zero gravity or artificial gravity? Can the human mind survive decades of confinement? Can a small group of humans maintain social cohesion and mental health over a lifetime journey? We think the answers are probably yes, with the right technology and support, but we're not certain. There are risks, unknown risks. And those risks add to the already daunting challenges of propulsion, energy, shielding, and all the other technical problems. So the realistic answer, the complete answer, is that a human could travel about 10 to 20 light years in a lifetime with foreseeable technology. But only if we solve not just the propulsion problems, but also the shielding problems, the radiation problems, the life support problems, and the psychological problems. All of them. If we fail at any one of these, the mission fails. If the propulsion works, but the shielding doesn't, the crew dies from radiation or micrometeorite impacts. If the shielding works, but the life support doesn't, the crew runs out of air, or water, or food. If the technology all works but the psychology doesn't, the crew becomes dysfunctional and the mission fails from social collapse. Every piece has to work, and that makes interstellar travel extraordinarily difficult. Not impossible, difficult. There's no way to avoid time dilation at high speeds. These are consequences of the structure of space-time itself, not limitations of our technology. Even an infinitely advanced civilization with unlimited energy and perfect engineering couldn't violate these limits without fundamentally changing the laws of physics. Some people speculate about wormholes, shortcuts through space-time that would allow faster-than-light travel without actually moving faster than light locally. If wormholes exist, and if they can be stabilized, and if they can be traversed safely, then yes, you could potentially travel vast distances instantly. You could step through a wormhole and emerge on the other side of the galaxy. But wormholes are purely theoretical. We have no evidence they exist. We have no idea how to create one or stabilize one if it did exist. The physics suggests that even if wormholes exist naturally, they'd be microscopic, short-lived, and completely useless for travel. To make a traversable wormhole large enough for a spacecraft, you'd need exotic matter, matter with negative energy density. We've never observed exotic matter, and we don't know if it exists. Some quantum effects produce tiny amounts of negative energy density, but nowhere near enough to stabilize a wormhole. So wormholes, while fun to think about, are not a realistic solution. The same is true for warp drives, Alcubierre drives, and other speculative propulsion concepts. They're based on solutions to Einstein's equations, mathematical constructs that are technically possible within general relativity. But they require exotic matter or negative energy, or other things we don't have and don't know how to get. They're not engineering projects. They're science fiction, at least for now. Maybe someday we'll discover new physics that allows faster-than-light travel. Maybe there's a loophole in relativity we haven't found yet. Maybe quantum mechanics, or string theory, or some future theory will reveal a way around the light speed limit. But based on everything we know today, based on a century of experimental confirmation of relativity, the speed of light is a hard limit, and that limit constrains how far a human can travel in a lifetime. So let's return to our question one more time with full honesty. How far could a human actually travel through space in one lifetime? The answer is somewhere between a few light years and a few dozen light years, depending on the technology available. With optimistic assumptions, fusion propulsion, efficient spacecraft design, maybe 20 light years. With conservative assumptions, nuclear thermal or nuclear pulse propulsion, maybe 5 or 10 light years. Either way, you're confined to the immediate neighborhood of the Sun. A tiny bubble in a vast galaxy. You could visit the nearest stars, explore their planets, search for life, establish small outposts, but you could never explore the galaxy. You could never visit the galactic core 26,000 light-years away. You could never reach the far side of the Milky Way. You could never travel to another galaxy. These places would remain forever beyond the reach of any individual human lifetime, unless you're willing to embrace time dilation and lose your connection to your own time. Then you could travel far, very far, but at a cost that most people would find unacceptable. This is the reality of interstellar travel. It's not impossible. It's constrained. Constrained by physics, by energy, by biology, by time itself. We can reach the stars, but only the nearest ones. We can explore space, but only a tiny fraction of it. We can send humans to other worlds, but they'll never see more than a handful of them. This might sound depressing. It might sound like a limitation, a boundary on human ambition, but I think there's something beautiful about it too. Because even though we're limited, even though we can't explore everything, we can still explore something. We can still reach beyond our solar system. We can still visit other stars. We can still search for life in the universe. And maybe, just maybe, that's enough. Maybe the goal isn't to explore everything. Maybe the goal is to explore what we can and to understand our place in the cosmos. To recognize both our potential and our limits. We live in a universe that is vast, almost beyond comprehension. Our galaxy alone contains hundreds of billions of stars. The observable universe contains trillions of galaxies. The total number of stars in the observable universe is estimated at around 1 septillion. That's 1, followed by 24 zeros. A number so large, it's meaningless to the human mind. And we, tiny creatures, living on a small planet orbiting an ordinary star, can only ever visit an infinitesimally small fraction of those stars. Even if we built millions of spacecraft and sent them in every direction at the maximum possible speed, we'd never come close to exploring even our own galaxy, let alone the universe. The universe is too big. Time is too limited. The speed of light is too slow. But here's the thing, we can still explore our neighborhood. We can still reach out to the stars around us. We can still search for answers to the biggest questions humanity has ever asked. Are we alone? Is there life elsewhere? What other worlds exist? What wonders await us in the cosmos? These questions can be answered within our reach, within the tiny bubble of space accessible to human travelers. There are dozens of stars within 20 light years. Some of them likely have planets. Some of those planets might be habitable. Some might harbor life. We could find out in a single human lifetime if we tried. We could send spacecraft to those stars. We could send humans if we built the right technology. We could establish a presence beyond our solar system. Not everywhere. Not throughout the galaxy, but somewhere. In a few places. A beginning. And maybe that's what matters. Not how far we can go, but that we can go at all. Not how much we can explore, but that we can explore anything beyond our own world. For most of human history, we were confined to Earth. We couldn't even reach the moon. Now, we've sent probes to every planet in our solar system. We've landed on Mars. We've flown past Pluto. We've sent Voyager into interstellar space. In the next century, we might send humans to Mars, to the moons of Jupiter and Saturn, maybe even beyond the outer solar system. And in the centuries after that, we might take the next step, the step into interstellar space, the journey to another star. It won't be easy. It won't be quick. It won't give us access to the whole galaxy. But it will be possible. And that possibility, that potential, is what makes this question worth asking. How far could a human travel in a lifetime? Far enough to reach the stars. Not all of them. Not most of them, but some of them. And sometimes, reaching for what's possible is more meaningful than lamenting what's impossible. The universe has set limits on us. The speed of light, the flow of time, the structure of space-time itself. These limits are real. They can't be wished away or ignored. But within those limits, there's still room for exploration. There's still room for discovery. There's still room for human beings to reach beyond their homeworld and touch other worlds orbiting other stars. A human lifetime is long enough to cross a few light years of space. It's long enough to visit a few nearby stars. It's long enough to search for life, to establish a presence, to begin the long, slow expansion of humanity into the cosmos. It's not long enough to see everything. It's not long enough to reach everywhere. But it's long enough to start. And maybe that's the real answer. Not how far we can go, but that we can begin the journey. That first step, from Earth to another star, is within our reach. It might take 50 years. It might take 100 years. It might take longer. But it's possible. And once we've taken that first step, once we've proven that humans can travel to other stars and survive, the rest becomes a question of time and commitment. Generation after generation, building on what came before, reaching a little farther with each attempt, one star at a time, one world at a time. Slowly, patiently, over centuries and millennia, expanding our presence into the galaxy. Not in one lifetime, not in 100 lifetimes. But eventually, that's the long view. That's the perspective we need when we think about interstellar travel. It's not a sprint. It's a marathon that spans generations. And the question isn't whether one person can run the whole race. The question is whether we, as a species, have the will to start running, to take the first steps, to commit to a journey that we won't live to see completed, but that our descendants might. Because that's what exploration has always been. It's always been about pushing boundaries, testing limits, going farther than anyone has gone before, even when it's hard, even when it's dangerous, even when the destination is so far away that the people who start the journey won't be the ones who finish it. We crossed oceans in wooden ships, knowing some wouldn't survive. We climbed mountains, knowing some wouldn't return. We went to the moon, knowing the technology was barely adequate and the risks were enormous. And we did it anyway. Because the drive to explore, the need to see what's beyond the horizon, is part of what makes us human. It's part of what we are. And now the horizon is no longer an ocean, or a mountain, or the moon. It's the stars. And yes, they're far away. Yes, reaching them will take decades of travel. Yes, we can only reach a few of them, but they're there. And they're within reach. And that's enough. So tonight, when you look up at the night sky and you see those distant points of light, remember this. Each one of those stars is a place. A real physical place where spacecraft could go, where humans could travel. Not all of them. Most of them are too far. But some of them, the nearest ones, the ones within a few light years, those are reachable in a human lifetime. With technology, we could build, if we choose to. The universe has given us a neighborhood to explore. A small neighborhood by cosmic standards, but a neighborhood nonetheless. Dozens of stars, potentially hundreds of planets, an entire region of space waiting to be discovered. We can't explore the whole galaxy. We can't visit every star, but we can explore our corner of it. We can visit our neighboring stars. And maybe, just maybe, that's exactly what we're meant to do. Not to conquer the cosmos, but to understand our place in it. Not to reach everywhere, but to reach somewhere. To take our first steps into a larger universe and see what we find. The answer to our question is both limiting and liberating. How far can a human travel in one lifetime? About 10 to 20 light years with realistic technology. A tiny distance in a vast galaxy. But it's not zero. It's not nothing. It's something. It's a beginning. And sometimes, a beginning is all you need.